Section A, Definitions and Basic Facts.
Welcome to the world of triangles. A triangle is a figure formed by three segments joining three non-collinear points, which means it's a three-sided shape. Everyone knows that. These three segments are called the triangle sides. Each side meets another at a vertex where they form an angle.
There are two ways to classify triangles, either by the lengths of their sides or by their angles.
First, by side length, we have equilateral triangles, which have three congruent sides, like triangle A here. All sides measure 4 inches.
There are also isosceles triangles, which have two congruent sides. Triangle B has two sides that equal 4 inches. We call the other side the base. The base can be on any side. Like, if we turn triangle B on its side or upside down, its base is still 2 inches.
Triangle C is scalene, which means it has no congruent sides. It's just a mess. It's all over the place.
So those are the 3 ways to describe triangles by the length of their sides. There are 4 other ways to classify them by angles. Let's take a look.
Equiangular triangles have all 3 angles congruent. In triangle D here, each angle measures 60 degrees. We'll see that all equiangular angles measure 60 degrees. Plus, notice that this is also an equilateral triangle. All equiangular triangles are equilateral, and vice versa.
Right triangles have one right angle. Other parts of right triangle E here are its 2 legs, which form the right angle, and the side opposite the right angle is called the hypotenuse. We'll talk more about right triangles later.
Obtuse triangles have one obtuse angle. So triangle F here has angles that measure 30 degrees, 35 degrees, and the obtuse angle, which is 115 degrees.
Acute triangles have 3 acute angles. Triangle G has triangle measures of 40, 60, and 80 degrees.
So now we know how to classify triangles, both by their sides and their angles. We can also classify triangles by their elements: earth triangle, fire triangle, air triangle, and water triangle. Get it? Elements: earth, air, fire, water. Now let's prove an important theorem about triangles that says the sum of the angular measures of a triangle is 180 degrees.
Remember that we haven't proven anything at all about triangles yet. The only things we know are they have 3 sides and 3 angles. Using inductive reasoning, we think that the measures of the angles of all triangles add up to 180 degrees. Using deductive reasoning, we're going to have to use what we already know about geometry to prove this.
Our theorem is the sum of the measures of the angles in a triangle is 180 degrees. Given that ABC is a triangle, prove that the sum of the measures of angle 1, angle 2, and angle 3 equals 180 degrees.
Now, for the first step of our proof, we state our given information. ABC is a triangle. For our second step, we got to do a little trick. We need to add a line to the diagram to help us prove our point. This is okay because we're not changing our triangle. The line we're adding runs parallel to segment BC. With this line, we'll be able to use the parallel line theorems we just proved, involving the relations of their angles. So, step 2 is we draw a line through A parallel to BC. We do this because of the parallel postulate.
Remember the parallel postulate? This is what all of Euclidean geometry is based on. It says that, given a line L and a point P not on the line, there is exactly one line M through P that's parallel to L. Lines L and M are therefore parallel.
Our next statement is the sum of the measures of angle 4, angle 2, and angle 5 equals 180. This is the definition of a straight angle. Don't be confused by the 3 angles here. In this diagram, we have 3 angles that make up the straight angle. Now let's go on to our next step.
Remember the alternate interior angles theorem? Lines are parallel if and only if alternate interior angles are congruent. The alternate interior angles theorem allows us to state that angle 4 is congruent to angle 1, and angle 5 is congruent to angle 3. Good deal.
Finally, because of substitution, we can state our goal. The sum of the measures of angle 1, angle 2, and angle 3 equals 180. You see how we substituted the information in our last step into the information in the step before it to get this answer? That's some snazzy proofing for you, and we're done.
So, why did we go through the trouble of proving that the angular measures of a triangle add up to 180 degrees? Well, the following statements can be proven based on the proof we just gave. These are called corollaries of the theorem. A corollary is an extra bit of information that can be proven along with the proof of our theorem. We want to know them because they can be used as reasons to prove other theorems. Let's take a look at them.
Our first corollary is, if two angles of one triangle are congruent to two angles of another triangle, the third angles are also congruent.
Isn't that amazing?
Our second corollary is, a triangle can have only one obtuse angle. If we have more than 90 of the 180 degrees accounted for by an obtuse angle, we have less than 90 degrees left for our other two angles, neither of which can be obtuse.
How amazing is that?
Our next corollary is a triangle can have only one right angle. If we have 90 of the 180 degrees accounted for by a right angle, we have exactly 90 degrees for our other two angles. So, the others could be 45 and 45 degrees, 60 and 30 degrees, or even 89 and 1 degrees. But there can only be one right angle.
Welcome to Planet Amazing.
Our last corollary is, the acute angles of a right triangle are complementary. So what this is saying is, by definition, we have 90 of the triangle's 180 degrees accounted for by the right angle, and we have 90 degrees remaining for the other two angles. The definition of complementary angles is two angles whose measures add up to 90 degrees.
Alex, I'll take amazing for 1,000.
So there we have it. We'll use these corollaries later on as we work more with triangles. In fact, let's use some of them now.
In this diagram, the exterior angle, angle 4, and angle 1 are supplementary. They form a straight angle. Therefore, the sum of the measures of angle 4 and angle 1 equals 180 degrees. Just like the sum of the measures of the angles of a triangle is also 180 degrees. Let's prove that the measure of angle 4 is equal to the sum of the measures of the two remote interior angles.
Remote interior angles? What the?
Oh yeah, remote interior angles are the two interior angles, angles 2 and 3, which are not adjacent to the exterior angle, angle 4. You see, they're remote.
So, the theorem we're trying to prove is the measure of an exterior angle is equal to the sum of the measures of the two remote interior angles. To prove that the measure of angle 4 equals the sum of the measures of angle 2 and angle 3, we're given the information that triangle ABC has exterior angle 4.
Let's set up a proof table. Our first statement is our given information. Triangle ABC has exterior angle 4. Second, we state that the sum of the measures of angle 1, angle 2, and angle 3 is 180 degrees. Our reason is this. The measures of the interior angles of a triangle add up to 180.
Our third statement is the sum of the measures of angle 1 and angle 4 equals 180 degrees. This is the definition of a straight angle.
Because the left-hand sides of the equations in steps 2 and 3 equal 180 degrees, we can combine them using substitution as our reason.
Algebra allows us to drop the measure of angle 1 on each side, leaving us with our goal. The sum of the measures of angle 2 and angle 3 equal the measure of angle 4. So we've proved that the sum of the remote interior angles is equal to the measure of the exterior angle.
All right, now that we know how to measure the angles of triangles, we're going to use this information to prove that two triangles are congruent.
Section B, proving triangles congruent.
What do we mean by congruent triangles? Well, we say that two triangles are congruent if and only if their corresponding parts are congruent. This is a very powerful statement. Let's see what it means.
Here are two congruent triangles. To precisely state their congruence, we say triangle ABC is congruent to triangle DEF. We can't say triangle ABC is congruent to triangle FED. Why? Well, let's see why.
By saying that triangle ABC is congruent to triangle DEF, we're saying that corresponding angles and sides are congruent. So, angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. Segment AB is congruent to segment DE. Segment BC is congruent to segment EF. And segment AC is congruent to segment DF. If we were to say that triangle ABC is congruent to triangle FED, We'd also be saying that angle A is congruent to angle F, which is wrong. Notice how we show what parts are congruent in the diagram? We mark them with little lines to show which ones match up.
Note that the definition, two triangles are congruent if and only if their corresponding parts are congruent, uses the phrase if and only if, reminding us that this statement is really two statements, the statement itself and its converse.
Our statement is, if two triangles are congruent, all of their corresponding parts are congruent. This statement will be very useful to us later on when we work out more proofs. In fact, we'll refer to this definition so much it's often given nicknames like the definition of congruence, fuzzy face, and CPCTC, which stands for corresponding parts of congruent triangles are congruent.
The converse is, if two triangles have congruent corresponding parts, then the two triangles are congruent. Because this statement requires us to find 6 matching pairs of items, all 3 pairs of sides, and all 3 pairs of angles, before we can claim that two triangles are congruent, it takes a lot more time than our first statement. We don't really need all of that stuff to prove that two triangles are congruent. Just wait, you'll see.
So let's do a few experiments to try to come up with 3 different postulates to use in our triangle proofs.
First, try this. Put your fingertips together like this. Now, bend the middle fingers together so the first knuckles are touching. Now, try to take your ring fingers apart without moving your other fingers. You won't be able to.
Try this. Take 2 drinking straws. Cut the first one into 3 pieces, one 4 inches, one 3 inches, one 2 inches. Do the same with the second straw so that you have 2 identical sets of 3 pieces. Make a triangle out of each set. Try to make the triangles look different. You won't be able to. If 2 triangles have the same side lengths, they will always be the exact same shape.
This is a key postulate in geometry, the side-side-side, or SSS postulate. So we don't need to match all 6 pairs of sides and angles. It's enough to just match the 3 sides to prove that the 2 triangles are congruent.
Side, side, side postulate.
Side, side, side postulate. If 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. The side, side, side postulate.
Let's try an example where we can put the side-side-side postulate to good use. This isn't a theorem we're proving, just a specific problem that you might find on a test. We'll use a proof table to work it out.
Given triangle QRS, with M as the midpoint of RS and QR congruent to QS, prove that triangle QRM is congruent to triangle QSM.
Note that we are not given the information that QM is the bisector of angle Q.
Let's set up our proof table. Our first step is to put down all of our given information. M is the midpoint of RS, and segments QR and QS are congruent.
Our second step is to state that segments RM and MS are congruent. That's the definition of a midpoint.
So, now we've got 2 pairs of sides congruent, the pair we're given, QR and QS, and the 2 that are divided by the midpoint, RM and MS. The only side left is QM, which is easy to prove. Because it's shared by both triangles, we just state that QM is congruent to itself by using the reflexive property.
Now that we've got all 3 sides congruent, we can state our goal. Triangle QRM is congruent to triangle QSM, thanks to the side-side-side postulate.
Pretty simple, huh? We've just used the side-side-side postulate to prove that 2 triangles are congruent. Now, let's take a look at the side-angle-side postulate.
We'll start with another experiment. Get a friend, 2 rulers, 2 protractors, 2 sheets of paper, a baseball, a glove, and a bat.
Pick 2 side lengths and 1 angle measure. Let's say the sides measure 4 inches and 7 inches, and the angle is 82 degrees. Now both of you draw triangles which have a 4-inch side, a 7-inch side, and an angle of 82 degrees between them. Your triangles should look the same. This illustrates another important postulate of geometry, the side-angle-side, or SAS postulate. Good job! Now go play baseball.
The side-angle-side postulate.
The side-angle-side postulate. If two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. The side-angle-side postulate.
Here we have two triangles that resemble the last pair. In fact, they went to high school together and ran in the same social circles. We'll use the side-angle-side postulate to prove they're congruent. What we need to do is prove that they have two congruent corresponding sides and one congruent angle in between. Given that AB is congruent to BC and BD is congruent to BE, we'll show that triangles BAD and BCE are congruent.
Let's get started by stating our given information. Segment AB is congruent to segment BC, and segment BD is congruent to segment BE.
So, we have been given two pairs of sides. To use the side-angle-side postulate, all we need to prove is that the angles between the sides, angle 1 and angle 2, are congruent. And we notice that angle 1 and angle 2 are vertical angles. Remember the definition of vertical angles? Vertical angles occur opposite each other when two lines intersect. And vertical angles are congruent. So, we can state that angle 1 is congruent to angle 2 because of the definition of vertical angles.
So, for triangles BAD and BCE, we have two sides and their included angles. We complete our proof by stating that triangle BAD is congruent to triangle BCE. Our reason is the side-angle-side, or SAS postulate. We're done!
Let's try one last experiment. With a friend of yours, agree on two angle measurements. Remember, they can't both be 90 degrees or greater, and one side length. Now draw a triangle starting with an agreed-upon side length and putting the agreed-upon angles at each end of the side. Say that you start with a 36-inch side. Put a 40-degree angle on one end and a 60-degree angle on the other. Now complete the triangles. Once again, your triangles should look identical. We have illustrated the following important postulate of geometry, the angle-side-angle, or ASA postulate.
Angle-side-angle postulate.
Angle-side-angle postulate. If two angles and the included side of one triangle are congruent to two corresponding angles and the included side of another triangle, then the triangles are congruent. The angle-side-angle postulate.
Let's look at the triangles here, ABC and EDC. Let's prove them congruent. Sound good? Great! Let's state our given information. We're given that AB and DE are parallel to one another and their lengths are congruent. We want to prove the triangles are congruent using the angle-side-angle postulate.
Let's get started by stating our given information. Lines AB and DE are parallel, and AB and DE are congruent.
Remember the alternate interior angles theorem? Lines are parallel if and only if alternate interior angles are congruent. Well, we'll use it for our reason in step 2. It lets us state that angles A and E and angles B and D are congruent to each other.
So, for each triangle we have a corresponding side, and two angles at its ends. By using the angle-side-angle postulate, we can set triangle ABC congruent to triangle EDC. Our goal is accomplished.
Now that we have some ways to prove congruent triangles, let's move on to using congruent triangles.
Section C. Using congruent triangles.
In the last section, we learned how to use three postulates that prove two triangles congruent. In this section, we'll also want to conclude that a particular pair of angles or segments are also congruent. We can do this because of CPCTC, or corresponding parts of congruent triangles are congruent. Let's start with a parallelogram, which is a four-sided polygon that has two pairs of parallel congruent sides.
Here we have parallelogram ABCD, which is cut by segment BD, making two triangles, BAD and DCB. We're given that segment AB is congruent to segment CD, and segment AD is congruent to segment BC. And we want to prove that angles 1 and 2 are congruent.
Do you see how we'll do this? We'll prove the triangles are congruent to one another. Then we'll use CPCTC to prove that corresponding angles 1 and 2 are congruent.
Let's start by stating our given information. AB is congruent to CD, and AD is congruent to BC. We have two pairs of corresponding sides, and we can get the third pair easily. With the reflexive property, we can state that the side shared by both triangles, BD, is congruent to itself. Now we have 3 corresponding sides.
With these 3 pairs of congruent corresponding sides, we can use the side-side-side postulate to conclude that triangles ABD and CDB are congruent. Because angles 1 and 2 correspond, our last step is to state that they're congruent because of CP-CTC. Corresponding parts of congruent triangles are congruent.
So, our good friend CP-CTC is pretty helpful once we establish that 2 triangles are congruent, because then there are all kinds of things we can establish as congruent. Sometimes we can even determine that a pair of lines are parallel by the CP-CTC method. Think about it. If we prove congruent triangles, then we've also proven congruent angles. If these angles happen to be corresponding or alternate interior angles, then the lines must be parallel. Make sense? Let's prove it.
Here's our pair of triangles. Given that LN is congruent to NQ and MN is congruent to NP, we'll prove that LM is parallel to PQ.
First, we'll state our given information. LN is congruent to NQ, and MN is congruent to NP.
Second, we know that angle 1 is congruent to angle 2 because vertical angles are congruent.
Now we have 2 pairs of sides and a pair of angles established as congruent. So we can say that triangle LMN is congruent to triangle QPN because of the side-angle-side postulate. We've got congruent triangles.
Because we have congruent triangles, we know angle 3 is congruent to angle 4 because of our good friend CP-CTC.
Finally, because angle 3 and angle 4 are alternate interior angles, we can state that LM is parallel to PQ. The reason is the alternate interior angles theorem, and we've proven our point.
Now, let's take a look at isosceles and right triangles.
Section D, isosceles and right triangle theorems.
So now that we have a good footing in the world of triangles, let's look at a couple of special types of triangles, the isosceles triangle and the right triangle.
We'll begin with the isosceles triangle. Remember isosceles triangle basics? An isosceles triangle is a triangle with 2 congruent sides. These 2 sides are called the legs. The third side is called the base. The angles formed by the base and legs are called the base angles, and the third angle is called the vertex angle.
Let's do a proof.
Given that sides AB and AC are congruent, prove that base angles B and C of isosceles triangle ABC are congruent.
First, we'll get started by stating our given information. Sides AB and AC are congruent.
Second, we'll draw AD, the bisector of angle A.
Why do we do this? We need a way to use one of our newly learned triangle postulates, side-side-side, angle-side-angle, or side-angle-side. Our reason is every angle has exactly 1 bisector.
The definition of an angle bisector allows us to state that angle DAB is congruent to angle DAC.
We can prove that side AD is congruent to side AD because of the reflexive property. Boy, that reflexive property sure is great.
We have 2 pairs of sides and the pair of included angles. So triangle ABD is congruent to ACD because of the side-angle-side postulate.
Now we can state our goal. Angle B is congruent to angle C because corresponding parts of congruent triangles are congruent, or CP-CTC. Done.
So we've proven that the base angles of an isosceles triangle are congruent. Let's try another theorem that'll prove that the legs opposite those congruent angles are also congruent.
We're given that angles B and C are congruent, and we want to prove that legs AB and AC are congruent in isosceles triangle ABC. Let's get started.
First, we'll state our given information. Angle B is congruent to angle C.
Next, we draw AD, the bisector of angle A, because every angle has exactly 1 bisector. I'm telling you, this is the key. Now, we've got 2 triangles to work with, and we're in business.
By the definition of an angle bisector, we know that angles BAD and CAD are congruent.
So far, this proof is really similar to the one we just did, which is fine, but we're going to change it up now.
Because we've just established that the two angles at the top are congruent and angles B and C are congruent, we know the third pair of angles must be congruent too. Our fourth step is to state the congruence of angles ADB and ADC. This is because the sum of angular measures is 180.
We want to use the angle-side-angle postulate. We have all the angles we'll need. Now we just need a side length.
To give us a congruent pair of sides, we state AD is congruent to AD. This is because of the reflexive property. There it is again, real handy.
Now we can state that triangle ABD is congruent to triangle ACD because of the angle-side-angle postulate.
Finally, we can say that AB is congruent to AC because corresponding parts of congruent triangles are congruent, or CPC-TC, and we've proven our theorem.
Nice job! In addition to our three postulates, there's a theorem we can use to prove triangles congruent. You may have noticed in our last example that having two pairs of angles and one pair of non-included sides congruent is good enough to prove congruent triangles. So here's our new theorem.
The angle-angle-side theorem says that if two angles and a non-included side of a triangle are congruent to the two corresponding angles and non-included side of another triangle, then the two triangles are congruent.
Angle-angle-side is a good theorem to remember, but you won't use it as often as the side-side-side, angle-side-angle, or side-angle-side postulates, so we won't take the time to prove it. Just keep it in your back pocket for later.
Just like a free lunch or a peace treaty called NITO, there's no such thing as a side-side-angle theorem. Here's why. This is an example of two triangles with congruent pairs of sides and a congruent pair of non-included angles. But the triangles are certainly not congruent. They're not even in the same ballpark.
For right triangles, there's a special theorem we can use to prove them congruent. It's called the hypotenuse leg, or HL theorem. Take a look.
To describe the hypotenuse leg theorem, we need to review a couple of terms related to right triangles. First, the two sides which form the right angle are called the legs. The side opposite a right angle and the longest side of a right triangle is called the hypotenuse. So, the hypotenuse leg, or HL theorem, states that if the hypotenuse and leg of one right triangle are congruent to the hypotenuse and a leg of another right triangle, then the two right triangles are congruent.
So let's consider the hypotenuse leg theorem with right triangles TUB and HOP here. We know that their hypotenuses are both 5 inches, and they each have a leg that is 3 inches. So, because they're right triangles, they're congruent because of the hypotenuse leg theorem.
There are 3 ways to describe triangles by their sides. Equilateral, with 3 congruent sides, isosceles, with 2 congruent sides, and scalene, with no congruent sides. We have 4 ways to describe triangles by their angles. If they have 3 congruent angles, they're equiangular. If they have 3 acute angles, they're acute triangles. If they have 1 right angle, they're right triangles. If they have 1 obtuse angle, they're obtuse triangles.
Corresponding parts of congruent triangles are congruent. This is also known as CPC-TC. We can also prove the congruence of triangles with the side-side-side postulate, the side-angle-side postulate, and the angle-side-angle postulate.
The angle-angle-side theorem says that if we know 2 angles and a non-included side of 2 triangles are congruent, then the 2 triangles are congruent. With right triangles, we can use the hypotenuse leg theorem.
Quiz 3.